Quantum computing. Quantum computing is the use of quantum mechanical phenomena such as superposition and entanglement to perform computation. Computers that perform quantum computation are known as quantum computers. Quantum computers are believed to be able to solve certain computational problems, such as integer factorization, which underlies RSA encryption, substantially faster than classical computers. The study of quantum computing is a subfield of quantum information science. Quantum computing began in the early 1980s when physicist Paul Benioff proposed a quantum mechanical model of the Turing machine. Richard Feynman and Yuri Monin later suggested that a quantum computer had the potential to simulate things that a classical computer could not. In 1994, Peter Shor developed a quantum algorithm for factoring integers that had the potential to decrypt RSA encrypted communications. Despite ongoing experimental progress since the late 1990s, most researchers believe that fault-tolerant quantum computing is still a rather distant dream. In recent years, investment in quantum computing research has increased in both the public and private sectors. On the 23rd of October 2019, Google AI, in partnership with the U.S. National Aeronautics and Space Administration (NASA), published a paper in which they claimed to have achieved quantum supremacy. While some have disputed this claim, it is still a significant milestone in the history of quantum computing. There are several models of quantum computing, including the quantum circuit model, quantum Turing machine, adiabatic quantum computer, one-way quantum computer, and various quantum cellular automata. The most widely used model is the quantum circuit. Quantum circuits are based on the quantum bit, or qubit, which is somewhat analogous to the bit in classical computation. Qubits can be in a 1 or 0 quantum state, or they can be in a superposition of the 1 and 0 states. However, when qubits are measured, the result is always either a 0 or a 1. The probabilities of these two outcomes depend on the quantum state that they were in immediately prior to the measurement. Computation is performed by manipulating qubits with quantum logic gates, which are somewhat analogous to classical logic gates. There are currently two main approaches to physically implementing a quantum computer: analog and digital. Analog approaches are further divided into the quantum simulation, quantum annealing, and adiabatic quantum computation. Digital quantum computers use quantum logic gates to do computation. Both approaches use quantum bits or qubits. There are currently a number of significant obstacles in the way of constructing useful quantum computers. In particular, it is difficult to maintain the quantum states of qubits as they are prone to quantum decoherence, and quantum computers require significant error correction as they are far more prone to errors than classical computers. Any computational problem that can be solved by a classical computer can also, in principle, be solved by a quantum computer. Conversely, quantum computers obey the Church-Turing thesis, that is, any computational problem that can be solved by a quantum computer can also be solved by a classical computer. While this means that quantum computers provide no additional power over classical computers in terms of computability, they do in theory provide additional power when it comes to the time complexity of solving certain problems. Notably, quantum computers are believed to be able to quickly solve certain problems that no classical computer could solve in any feasible amount of time, a feat known as quantum supremacy. The study of the computational complexity of problems with respect to quantum computers is known as quantum complexity theory. Quantum gate array computation decomposed into a sequence of few qubit quantum gates. One-way quantum computer computation decomposed into a sequence of 1 qubit measurements applied to a highly entangled initial state or cluster state. The adiabatic quantum computer, based on quantum annealing computation decomposed into a slow continuous transformation of an initial Hamiltonian into a final Hamiltonian, whose ground states contain the solution. Topological quantum computer computation decomposed into the braiding of anyons in a 2D lattice. Please subscribe, like video, share, comment and click bell icon for upcoming videos.